Welcome everyone. Before I get started, I just want to say thank you to Sierra Circuits for allowing me to present today, and also for all of you for attending. So yeah, it's exciting. A little bit about myself. My name is Jose Garcia, and I'm a member of Uyemura USA. I work as a senior field engineer in the Northern California region. My working responsibilities include process troubleshooting, process reviews, chemical installations, and assisting customers with root cause analysis. I earned my Bachelor's of Science in Chemical Engineering from San Jose State, and I also hold a Lean Six Sigma Black Belt certification. Now, today's agenda includes one, Sierra Circuits, an outside-in look; two, an overview of Uyemura and when the company got started; three, we'll cover conventional final finishes for space and RF applications; four, we'll also discuss advanced final finishes for space and RF applications; and lastly, we'll conclude with a Q&A session. Now, Lucy, do you want to expand a little bit on Sierra Circuits?
Yes, thank you. So very quickly, for those of you who don't know Sierra Circuits, we are a PCB manufacturer and assembler. We do everything made in the USA. We build our bare boards in Sunnyvale, California, and our assembly house is in San Jose. We do pretty much every type of boards, so HDI, flex, rigid, RF, microwave, micro. We are known to handle very complex projects. So, if you have very complex and advanced layouts, just talk to us and we can probably do something about it. We work with every industry, from space and defense to medtech, telecom, automotive. And we have Steve Carney also here in the webinar with us. So if you have any questions, Steve is the R&D manager at Sierra, and he can probably answer.
All right, thank you, Lucy. Now, moving on to an overview of Uyemura. Uyemura Central Research was established in 1848 in Osaka, Japan. Uyemura is a 550 million US dollar per year chemical supplier to the electronics and specialty chemicals industry. The Central Research Laboratories have over 70 full-time research and development employees, which focuses 100% on metal deposition. So in other words, no dry films, laminates, solder masks, developers, or resist strippers. The lab personnel work with, of course, these Uyemura chemistries, and as well as process equipment and controllers that are compatible to operate and monitor these chemicals. Now, on the right-hand side, we have Uyemura USA, which was established in 1985 in Southington, Connecticut. Our vision is to be North America's leading supplier of technologically advanced products, innovative solutions, superior technical support and training for our customers in the electronics and specialty chemical industries. Markets served include printed circuit boards, semiconductors, advanced packaging, memory disks, and general metal finishing. Our value proposition at Uyemura is to help North America's electronics and specialty chemical industries mitigate risk by solving problems and adding value. Now let's cover an ENIG and ENEPIG process overview. So ENIG stands for electrolysis nickel immersion gold. Adding the electrolysis palladium um, will provide the ENEPIG final finish process. Now the process goes from left to right, as you can see in the blue arrow, and it starts with a cleaner. This helps reduce surface tension on the board and also removes palladium from non-plated through holes. The Cascade DI water rinses are used throughout the process to ensure that we basically eliminate dragged-in chemistry for the purpose of avoiding cross-contamination of the other chemicals. Now, an edge bath is then used. This edge bath will help smoothen the copper And this will remove approximately about 1 to 1.5 microns of copper thickness. Now, a hot sulfuric bath may also be implemented, as you can see on the bottom left there, especially when working with thick panels that have the through holes. This way you can flush out any remaining edge solution. And really by doing this, it helps avoid the issues of uh, skip plating, if you haven't heard of it, which pretty much involves some of the areas of the substrate to not undergo ENIG or ENEPIG plating. Now, the sulfuric acid pre-dip is a common ion dragon. And then next you move on to a palladium-based activator, which will deposit a palladium seed layer of approximately 100 angstroms in thickness onto the panels. Now the sulfuric acid post-dip will then be used to remove any excess palladium, especially in the thicker panels that have those through holes. Now in the green there, we have the electrolysis nickel bath itself. It's made up of nickel metal content, reducing agent, chelators, stabilizers, and also pH regulators. And these pretty much will all work together to ensure that we deposit our nickel layer onto our substrate or panels. Now on the bottom right hand side there, you see the electrolysis palladium that can also be implemented. And it's better for corrosion resistance as compared to ENIGs, just due to the nickel being 3 times more easily displaced compared to palladium when you're going through immersion gold. And I'll be covering an explanation on nickel corrosion. I'll go over the mechanism later on in this presentation. Now, the metal deposition is finalized at the very end with the yellow there in the immersion gold, which involves a displacement reaction, where essentially your gold layer is deposited onto the nickel surface and simultaneously displaces nickel ions in solution from the nickel surface layer. All right, now let's discuss electrolysis nickel. So these two products here are two of our over 20 electrolysis nickel products at Uyemura. The NPR4 deposits 6 to 9% by weight phosphorus. It is skip and corrosion resistant and has excellent stability and resolution. Now the NPR8 is a newer generation bath and deposits 7.5 to 10% by weight phosphorus. By having a lower stabilizer content and also depositing a higher phosphorus content compared to the NPR4, this NPR8 bath provides enhanced corrosion resistance and higher plating initiation on the substrate or panels. Now this bath also has improved tolerance to dry film resist for the selective finishes. And to finalize there, the NPR8 also has excellent stability and resolution. Now the top-down SEM image that you see with the red arrow shows the structure of the nickel surface. And the very right-hand side cross-section image provided there is etched to highlight the nickel grain structure. Now ENIG is a conventional final finish. Advantages of ENIG are that it has excellent coplanarity, has good plated through hole coverage, has a long shelf life, is universally accepted, and is aluminum wire bondable. Also provides reliable solder joints. Now, disadvantages are that it can have a higher cost associated to it. It is not reworkable. It gives a higher signal loss compared to other finishes, is more susceptible to nickel corrosion, and can be a more complex process. Now, this ENIG final finish follows IPC 4552B, which is the specification for ENIG plating on the PCBs or printed circuit boards. Now, the IPC basically is the committee, right, that was put together to just ensure that we have reliable and high quality electronics. And that's why a lot of these final finishes or the conventional ones will have the IPC specifications that you'll see and I'll be covering as well. This particular IPC 4552B states that you should be between 3 and 6 micron of nickel and 0.04 to zero point 0.1 microns of gold. Now for the ENEPIG IPC requirements, we put a table together. So I'll just go over a quick overview of this. But starting with the XRF certification, it is used to basically make sure that our measurement tool is capable of taking ENIG thicknesses and minimizing or really trying to eliminate high variability. The XRF tool is ideally set up with using a type 1 gauge study. And this involves using the XRF with a single operator who will take a minimum of 25 measurement readings of a reference standard. Now, the two things to look into are one, the accuracy, which is basically the variation between the measurements and the reference standard, and two, precision, which is the variation between repeated measurements. Now, looking at column 2, deposit thickness distribution is also important to be analyzed. Now, ensuring that there is no high variability between the edges, center, and both sides of the substrate is crucial as well. We just want to make sure that everything is, for the most part, uniform in thickness. Now, visually, the substrates should also look uniform in the complete ENIG coverage. And then in the through holes as well, right? We want to make sure that all of that is uniform and there's no any weird looking gaps in between that don't have ENIG plating. Now, corrosion analysis is also completed for ENIG finish, and I'll go into that as well in the upcoming slides here about what nickel corrosion is and how it works. Now, there are more listed items, as you can see, shown in the table here, but two areas that I do want to highlight are items 5 and 6, which deal with reliability. So meeting both of these specifications that you see on the right-hand side, the MIL standard 883, which covers military and aerospace criteria, and the J standard 003D, which covers solderability tests, will ensure that your products have high reliability. So the testing is basically adding stress to these PCBs final finish, pretty much to determine the lifespan of the boards during the high stress conditions. Now, as mentioned earlier, for ENIG, in this case, the immersion gold will displace the nickel, right? The nickel gives up electrons if there is an accepting species, which for ENIG involves the gold. Now, shown in the picture on the top left, the deep crevice lacks gold, which then allows for the positively charged hydrogen ions to pick up the electrons and cause the nickel to corrode without the gold deposition. And then this ultimately leads to a deeper gap, which you can see there on the bottom left. Now, on the right-hand side, there are several corrosion ratings, which are categorized by IPC 4552B. And we start with level 0, which is basically categorized as being defect-free. There's no nickel corrosion spikes, and it looks pretty smooth, as you can see on the image. Now, level 1 is when there are a number of defect spikes, and it's less than the quantity of 10. And also making sure that those spike depths are no more than 20% of the nickel deposit thickness. I'll jump into the last one there, which is level 3. And the number of spikes, defects are categorized as being over 10, which also take up 40% of the nickel thickness deposit. Or if you also see black band, which is observed and extends 30% of the field of the cross section there. Now, level 2, I kind of skipped over that one just because IPC does specify that level 2 is categorized as anything between level 1 and level 3. So that's kind of why I jumped over that one. But yeah, if you reference IPC, that's what you'll see. And then in conventional ENIG finishes, especially with ENIG being developed, it was more prone to corrosion. However, nowadays, corrosion has been studied and it's better controlled with newer chemical bath formulations, With these studies conducted, the IPC committee did determine that all the levels can be acceptable, but again, you would have to reference the IPC specification for those specific criterias. Now, one of the important things though here is making sure that we reduce and eliminate corrosion on nickel is very crucial to avoid our poor bond between ENIG with wire bonds and solder joints, just to further guarantee that we have high reliable products. Now, ENIG is another, or ENEPIG, sorry, is another conventional final finish. Advantages of ENEPIG are that it has excellent coplanarity. It has good plated through hole coverage, has a long shelf life, is universally accepted. It is gold and aluminum wire bondable, and provides reliable solder joints. Some disadvantages include it being higher in cost. It is non-reworkable, gives a higher signal loss, and it can be a bit more of a complex process. Now, the ENIPIG is governed by the IPC 45526, which is the ENIG plating for PCBs, essentially. Now, similarly to the ENIG review that we discussed earlier, the IPC committee did come up with this specification to ensure the high reliability for the PCBs, and the thicknesses are, as you can see for the nickel, is very similar with the 3 to 6 micron. However, with the palladium, you're going to go from 0.05 to 0.3 microns, and gold from 0.03 to 0.07 microns. Now here, as you saw with ENIG as well, we put a table together for the IPC requirements. And after plating ENIPIG, we just want to make sure that we have complete ENIPIG coverage on the substrate. Also on the plated through holes themselves, want to make sure that that has complete coverage. Now, thickness distribution should also meet the IPC criteria for nickel, palladium, and gold, from front and back and center and edges of the panels. Now, thickness distribution is important just to make sure that, again, you just don't have any wonky different results throughout the panels. But then lastly, again, just to tie this into the reliability, right, is we want to make sure that military standard 883 is met and J standard 003 is met, just to check off the boxes for any military and aerospace requirements and solderability as well. Now, here we have a comparison between palladium phosphorus to pure palladium in ENIPIG. There are differences in the deposit structure, as you can see in the cross-section images. Palladium phosphorus is amorphous in nature, while the pure palladium is crystalline in nature. Palladium phosphate deposit has a slight advantage for solderability, while the pure palladium has a slight advantage for wire bonding. Now, when comparing both of them, IPC 4556 does state, based on studies conducted, right, that both of these palladium deposits have no perceivable differences in their reliability performance. All right, now moving on to the last conventional final finish is our silver immersion. Now, the advantages of this final finish include a good coplanarity. It can be used in a vertical or horizontal process configuration and is reworkable. The downsides or the disadvantages are that it can include a sensitivity to handling, attack on the solder mask interface, and is susceptible to creep corrosion and champagne voids. Now, a quick overview on the process for silver immersion. We start with cleaner. We move into an etch, go into the pre-dip, and then plate with silver immersion, and then lastly applying a anti-tarnish coating to that. Now, the specification for silver immersion is IPC 4553A. And per the specification here, we want to make sure that we're between 0.1 to 0.3 microns of silver thickness. Now, IPC requirements were just shown here as well, just to kind of give you an overview of what is entailed in the requirements for silver immersion. And again, as you can see, there's very similar things that are looked at, right? The complete coverage, making sure that we have a good distribution, there's no solder mask peeling, and then also meeting the solderability requirements, which I mentioned earlier, the J standard 003 D. Uh, One other thing that I wanted to mention was for silver immersion, handling and packaging is very important to avoid tarnishing of the product. Silver immersion plated boards are sensitive to exposure of contaminants. This is why that IPC 4553A mentions that the board should be kept in a non-corrosive environment, and also the listed packaging and handling requirements should be followed as well, and those can be found in IPC specification for silver immersion. All right, now let's move on to some technological trends. So what we are seeing is the need for increasing or better performance, reworkable products to avoid losses in cost, higher in both reliability and life expectancy. There is also a trend to decrease product sizes, decrease the weight of the products, and decrease the amount of power needed. And lastly, also of lowering down manufacturing costs. Signal integrity has also been a major topic of discussion and really continues to be studied extensively. Now, on the bottom right-hand side there, you see the chart that represents stresses that are applied onto products due to conditions like thermal conditions, on and off power cycles, bending, and really other stress performance features. Now, as various stresses are applied, the strength of those products also need to increase to withstand the high stress conditions. Now, by keeping up with the strength demands due to the stresses applied on the products, it will help us minimize any defects from occurring. Now we move on to the advanced final finishes. We start with the thin ENEPIG, which is short for electrolysis nickel, electrolysis palladium, immersion gold. EPIG, short for electrolysis palladium, immersion gold. EPAG, electrolysis palladium out of catalytic gold. And EGIPIG, immersion gold, electrolysis palladium, immersion gold. ISIG, which is immersion silver, immersion gold. And then also DIG, which is direct immersion gold on copper. And now here on the right-hand side is a table of various final finish industry users. General printed wiring boards, main attribute is functionality. All final finishes are used with the exception of EPAG. It really is not because just due to the higher buildup of gold, which attributes to higher costs, basically. The semiconductor and packaging's main attribute is fine line and high temperature reflow. The most commonly used final finishes are thin ENEPIG and IGIPIG, while the others listed final finishes are moderately used, represented in the yellow. Now, 5G's application's main attribute is high frequency. All final finishes are used, and the thin ENEPIG is moderately used. The medical industry's main attribute is to be nickel free. Therefore, all the final finishes are used except the ENEPIG. And then we have military and aerospace's main attribute is reliability, which uses all the listed final finishes, but moderately uses ISIG. Now, the ENEPIG for thin nickel advantages include excellent coplanarity, fine line resolution, it is economical, has good signal integrity, a good shelf life, is gold and aluminum wire bondable, and provides reliable solder joints. Some disadvantages are that it is a complex process. It is sensitive to solder mask leaching. There is no universal acceptance at the moment, and there is currently no control of nickel thicknesses. Now, by there not being an IPC specification for thin nickel final finish, some thicknesses that have been tested fall in the ranges here that you see, the 0.13 to zero point 0.2 microns of nickel, 0.08 to 0.13 microns of palladium, and gold as well, the thickness. Now here we have wire bond test results in comparison between thin nickel and standard ENEPIG. The conditions of the testing were using 1 mil gold wire on as plated or as is samples, and then samples that were heated at 175 degrees Celsius for 16 hours. Now these comparisons were made on different Uyemura palladium and electrolysis nickel products. The overall performance between thin nickel deposit to normal nickel deposit in the ENEPIG are very similar with no significant differences. The failure modes are also very similar between both finishes as well. Now here we have gold deposition modes. One, we start with immersion gold. It's a displacement reaction where the reduction of the substrate supplies the electrons needed to reduce the ionic gold to metal. It is a limited thickness capability as the substrate becomes less available and may cause some corrosion. Two is the autocatalytic gold. The electrons needed to reduce the gold ions to metal are supplied by a reducing agent component in the bath. This requires an underlayer of immersion gold to initiate. It is non-aggressive and will not produce substrate corrosion. Theoretically, it can have unlimited thickness and keep plating. And then three, we have reduction assisted immersion gold, also known as RAIG. And it's a mixed reaction bath. Both immersion and autocatalytic reactions start simultaneously. As the substrate becomes less accessible, the immersion reaction will diminish and the autocatalytic reaction will dominate. It's non-aggressive and will not produce substrate corrosion. It is also capable of depositing 0.1 to 0.15 microns of gold in a single step. Now, Uyemura developed a newer generation mixed reaction mixed reaction gold bath, the one that you see here, the TWX42. So a displacement reaction initially takes place with the on the nickel surface, as shown in the illustration here on the left. The reaction builds up 20 to 30 angstroms of gold, and then an autocatalytic reaction takes over to build the remaining gold thickness. A benefit of this bath is not needing to complete cyanide dosing, as was the case with older generation gold baths. And then regarding the reliability, this bath is essential just because it's near neutral and it can avoid nickel corrosion. Now, benefit of the RAIG baths is that they can be used with most of the conventional final finishes like ENIG and ENEPIG, as well as some of the advanced final finishes. Now, EPIG and EPAG, we have advantages being having an excellent coplanarity, having fine line solution, having a good shelf life, good signal integrity, is gold and aluminum wire bondable, and provides reliable solder joints. The disadvantage is that it can be higher in costs, non-reworkable, more complex process, and it's not universally accepted yet. And these thicknesses shown below are the ones that have been tested, but currently there is no IPC specification for these finishes. Now here we have a high-speed shear results for EPIG and ENEPIG, a comparison. Now the right-hand side shows the thicknesses that were tested. The conditions involved during the testing were having used the SAC 305 solder with as is plated boards, and also the boards that went through a heat treatment for 300 hours at 150 degrees Celsius. ENEPIG resulted in a higher reliability as compared to EPIG when looking at the shear strength results. Now the energy results also indicate that the EPIG solder balls will break with less energy as compared to ENEPIG. and which basically makes ENEPIG a little bit more reliable. Now let's go over wire pull wire pull test results. Now this slide, I'm sorry. Um, ISIG, we have advantages for this. And by the way, ISIG stands for immersion silver, immersion gold. Some advantages are that it has excellent coplanarity, has fine line resolution. It is production proven at the moment, has good signal integrity, is gold and aluminum wire bondable, has or provides reliable solder joints. Disadvantages are that it can be a complicated process and gives off champagne voids as well. Now the process sequence is going from starting at the cleaner, etching the copper, going into a nitric based pre-dip, plating with silver immersion, and then applying a flash gold, and then also finishing off with a thicker gold deposit. Now these thicknesses are what have been tested with ISIG, which ranges from 0.1 to 0.3 microns of silver and 0.1 to 0.15 microns of gold. Now here we have ball pool strength results for ISIG at 1 and 5x reflow at 240 degrees Celsius. The pull strength results are very similar. The failure modes did show some differences. And all the sample failure modes were mostly at the solder. However, both the 0.3 micron silver plated samples showed some voiding, while the 0.1 micron silver plated samples kept most of the IMC. Now, gold wire bonding testing was also completed on ISIG. The conditions for this testing was using a 1 mil gold wire, no heat treated samples, a sample baked at 155 degrees Celsius for 4 hours, and then also a sample baked at 155 C for 8 hours. Now, the results showed no liftoffs, so that was definitely a good positive sign, making sure that we have good reliability. So yeah, there was no liftoff from the bonds. Now, direct immersion gold onto copper, we have the advantages, which are having excellent coplanarity, has fine line resolution, is economical, has good signal integrity, a good shelf life, um, gives gold and or is gold and aluminum wire bondable, and provides reliable solder joints. Now, some disadvantages are that it is not universally accepted, uh, has been has been has seen copper diffusion into the gold, and it is not aluminum wire bondable at greater than or equal to zero point 0.1 gold microns of gold. Now, what is nice about the DIG is that we have a more condensed process sequence, as you can see on the bottom there. By it being nickel free, also, it helps with the topic of insertion loss applications, and as well as you can see the DIG that has been tested or seen with these thicknesses that you see on the screen. Now, what is DIG? It is direct immersion gold onto the copper surface. The DIG is available as the conventional displacement reaction or by the RAIG that uses the initial displacement reaction followed by an autocatalytic gold reaction. The two products that you see here, the TCU38 and the 41, are two of our Uyemura products that are commonly used for DIG applications. Now, some benefits and uses are on the right-hand side here that you see no need for nickel in high-frequency applications where nickel causes the interference. It is compatible with lead-free solder. It helps with reducing voids. and can be used for various applications, including wire bonding and electrical contact. Can be used for printed wiring boards, flex printed wiring boards, and the integrated circuit substrates applications as well. Now, during wetting balance of the DIG finish for 4 tests that were completed, the testing involved with soldering SAC 305 at 255 degrees Celsius using 0.5% activation flux. The conditions of the samples analyzed were as received, and also samples after 1, 2, and 3 reflows. The as received sample showed the highest wetting force. And as you can see in the blue there, after 3 reflow sample showed the least wetting force. But however, all the tests had acceptable results overall. Now, solder ball pool testing was also completed with using SAC 305 at 150 degrees Celsius with samples at 2 different gold thicknesses that you can see here on the left, 0.06 microns and 0.2. And as the graph shows, both of them, if you overlap those, you can pretty much see that there is insignificant differences in the ball pool strength when comparing both of those gold thicknesses. Now, moving on to insertion loss. So as it reads here, in telecommunications, insertion loss is the loss of signal power resulting from the insertion of a device in a transmission line or optical fiber and is usually expressed in decimals. Now, currently there are efforts in the topic of insertion loss. HDPUG, which is an organization, the long name is High Density Packaging User Group, is a collaboration between companies that include chemical suppliers, material suppliers, OEMs, and PCB manufacturers. Basically, there's an ongoing project investigating final finishes that can best help minimize high frequency signal distortion. Now, here is a comparison chart for insertion loss for different final finishes. When taking a closer look at the insertion loss at the 10 gigahertz and 30 gigahertz that are in red boxes, the ENEPIGs and ENIG show more insertion loss as compared to the advanced final finishes. The comparison plot really shows that eliminating the nickel layer will help minimize insertion loss. And overall, there continues to be those major efforts made into lowering the insertion loss or the high frequency insertion loss. This is why alternative finishes, again, just continue to be investigated. This has been a very ongoing project, and there have been a lot of efforts in trying to see what best works for this particular topic. Now, again, thank you, Sierra Circuits, for this opportunity of presenting today, and thank you all for being here. Now, if you have any questions, yeah, please let me know. So I am interested in the effects of finishes on adding surface roughness to HVLP type coppers that will increase loss for our high-speed SERDES. Can you provide or point to info on this particular interest in finishes, other processes on roughness when we have 6 or 7 consecutive layers of signal layer microvia HDI? My understanding is that treatments done for these types of layers can significantly increase roughness and loss. Is this the case? Yeah, well, I do know that with adding surface roughness to coppers, you technically will get a bit of a signal integrity compromise, right? But I guess it's just not very clear. I don't finish.
Yeah, let me, I think I know where he's going with that, Jose.
Oh,
All right,
go ahead, Rich.
so,
Yep.
yeah, so, look, there are 3 major contributors to signal loss, right? There are the materials, which is the highest percentage, very important to choose the right materials in order to lower the insertion loss. And there are many, many materials to choose from, etc. The second, as stated, is the roughness of the copper. Okay, clearly, coppers which are less rough. In fact, many people use, annealed copper specifically for that and reduce the roughness on the internal layers in order to reduce the insertion loss. Now, on the outer layer, it would be very good to reduce the roughness as well. So you need to make sure you're choosing micro etchants in many cases, like some of the mech products, where the smallest amount of roughness is imported in order to get that good adhesion for the fine lines. And the last thing that I know you're familiar with is the use of, and maybe you want to comment on this, the use of peroxide sulfuric as a smoothing and leveling etchant, in order to reduce that roughness. So within the micro etch that you described, we really like to move towards the peroxide sulfurics in order to kind of level out the copper. So those are all the things that you do. Again, roughness of copper is a major contributor to signal loss. In fact, it would have a much more significant impact than the final finish on insertion loss. So when you get above 40 decibels, you just got to get everything right. You got to have the right materials, you got to have non-rough copper, and you have to choose the right final finish. Okay, so it's kind of all three things. Every presentation I've seen on this particular subject says the same thing, and that's that above 40 gig, you need everything right in order to deliver the performance that they're looking for.
I have some comments on this because we look at this every day. So he's primarily talking about roughness on inner layers. Mm-hmm. So you have very low profile copper foil. So you have the copper foil. It has a dendrite structure on one side of it, and that's what the very low profile is. Then you also have the alternative oxide adhesion promoter that we put on the smooth side of the copper prior to lamination. So both of those have an impact. On the very low profile, you can specify. The bonding adhesion promoter, alternative oxide, that we put on, we control that. There's some new chemistries coming out that limit that buildup. The only thing with that is there's trade-offs on both the low profile dendrite structure and what they're using for the adhesion promoter. Because the less you have, the more prone to delamination. So there's a number of things that you can do here in the stack up, like spread glass supports better adhesion. So it's really just controlling everything. But yes, it is it is an issue for each inner layer. That's it.
Yep. Yeah. Thanks, Steve. I love the detail that you got into. It's consistent with what I described, and thank you for the additional detail on the inner layers.
So one thing we are looking at is doing fully additive. This gets into ultra high density, but we're looking at embedded trace technology that you don't need it doesn't use foil, it's a fully additive. So you don't use the dendrite structure on the foil, nor do you need the adhesion promoter on the surface. So anyway, we're looking at getting rid of that, but it is a problem.
The question is your XRF inspection done by human? And is it a process verification, for a batch order sample on all batches of boards. The XRF inspection, I'm assuming, is whenever you need to set up. But the XRF inspection is done by human when you're taking measurements, and is the process verification or batch order sample on all batches of boards. So yeah, the XRF inspection, how, if I'm understanding your question correctly, you're basically taking measurements of the panels, right? And just taking 60 by 60 mil dimension pads. And typically it will also depend on the requirement of the customers. Some customers of class 3 will require for more batches to be checked, while maybe lower class customers might not have as much requirements. It just kind of depends on the application and how less variation you might need for one application versus the other. I have following questions. One for ENIG finish. Who does the corrosion monitoring? PWB manufacturers, monitors, or Uyemura helps with PWB manufacturers? So to answer that first question, we do recommend doing in-house corrosion monitoring. Uyemura will provide this assistance as well with checking samples maybe once a month. But for the most part, it will be good for faster results as well to check in-house just to make sure that you don't have corrosion or limiting that happening. Now, number 3 is we have a choice between ENIG and ENEPIG on our space application printed wiring boards. Which finish is the clear winner? Not considering the cost, reliability of solder joints is the more important one. Well, ENEPIG does help out with limiting that corrosion. So in terms of reliability, I think ENEPIG will be the winner there. Now, Daryl.
Yeah, Jose, on the lead, I mean, both ENIG and ENEPIG are qualified for military applications. There was some early work which did show that there was a slight that ENIG had a little bit better shear forces and ball pull on lead solders versus ENEPIG, but they were all within range of specification, and both processes are highly reliable.
Oh, perfect. Thank you, Rich.
Yeah, and the lead is mostly for military application.
Yep.
Like Raytheon, etc. All of those products are all ENEPIG type. Okay.
Okay.
Sorry.
Thank you, Rich.
Yep.
Daryl, thank you for your question. Your question is, your DI wash, is it a daily verification of purity or a process done a few times a year? Now, DI wash, I'm assuming you're talking about the rinses. We just want to make sure that we have low conductivity coming into the process from the DI containers or the reservoir. And as far as whenever you're rinsing as well, because you're going to have dragging of the chemistries, conductivity will be going up. But that is why you will also have a turnover of the DI rinses. Typically, we will start at like 3 gallons per minute. And just to make sure that we have enough turnover and limit that the conductivity buildup in the rinses.
Thank you very much, everyone, for joining. Thank you so much, Jose, for presenting this great webinar. And I will send the slides and recording this afternoon. Thank you, everyone. Have a great day. Bye-bye.
Yeah, thank you all.